Mr. Adhikari.
Thank you, Chair. I'd like to thank the organizers for inviting me and letting us present our work that we're doing, along with my colleagues here from CNR and EVK2 CNR and Nepal Academy of Science and Technology, our collaborator in Nepal. First, a brief introduction about my organization. I work with EVK2 CNR. EVK2 CNR started out, now is celebrating 25 years of work in the Himalayas, Karakoram, and elsewhere in the globe. It started out as a simple expedition trying to measure the height of Everest and K2 in Pakistan using GPS at the time, which was a novel technology. Since then, it's evolved into a scientific research organization for focusing on mountain issues. We work on atmospheric climate, water, glaciology, biodiversity, and anthropological issues, but focused on mountain areas. The flagship project of EVK2 CNR is the SHARE, which is stations at high altitude research on the environment. And the most visible lab that we have is in the shape of a pyramid. I show a better picture towards the end, and is located at 5,050 meters altitude. This is Everest Peak here, and this is where the Pyramid Lab is. It is the highest global atmospheric watch station, and is the 34th station operating throughout the world. Data from here, at least the atmospheric science data and the meteorology data, are webcasted real time through this website, and if anybody is interested can look at not just the data but also live webcast of image of Everest, which is refreshed every few minutes. So if you want to look at how Everest is looking at the current time, you can do it. Now EVK2 is operating a lot of stations throughout the globe, but again focusing on mountain areas. We have several stations in Nepal, starting from an altitude of 2,600 meters. And for a few years, we operated a weather station at South Col at 8,000 meters. And then there's a vertical gradient here, which is very exciting to study. We have a bunch of stations in the Italian Alps, a few stations again in Pakistan, and we've just started a station in Mount Rwenzori, Africa, and in the Andes. Just to present some data since we're talking about the Nepal Himalayas, I'm only showing data from the Nepal Himalayas, mostly meteorology and the short-lived climate forces that we're talking about today. But here at the Nepal, we have data for meteorology for almost 20 years, but since we're talking about pollution, I'm only showing the 6 years because we have data for the last 6 years, starting from 2006, for the short-lived climate forces as well. And as you can see in the data here, even at 5,000 meters, if you look at the temperature, there's significant time here during the summer monsoon where the temperature is above freezing, and that correlates to rain precipitation here. Currently, we don't do any snow measurements, so we don't have solid precipitation, but rain, as you see, also has distinct seasonality only during monsoon, and not so much during the winter where there's more snow. In terms of relative humidity, at that high altitude, again, we have very high RH during monsoon, and then very dry in the winter. Wind speed, when I presented this result during the ACAM Asian monsoon, people were saying, your wind speed is clearly wrong, it's very low. And at first it seems like, okay, 500 millibars, it ought to be higher, but we have several stations operating in Pyramid, and they all show that it's pretty low because we're still on the ground. Yeah. And in terms of wind direction, is mostly southerly. Again, since we're talking about short-lived climate forces, I'm showing data for ozone and black carbon, the two main climate forces. And here again, you see a distinct seasonality. A colleague of mine analyzed 2 years of data, and what he published, which was quite surprising even to me, was in the 2 years of data that he analyzed, only 14% of the days were found to be stratospheric events. So that's ozone coming down from the stratosphere. So if we're getting high ozone, 80 ppb, and only 14% is stratospheric, where is all the ozone coming from? You know. And again, these data are available at the GAW website, data set for greenhouse gases. If you look it up, you can look at the data. Black carbon, starting from 2006, again 2012, shows similar trends, peaks in the pre-monsoon, and then low levels. Here I'm showing daily averages, but if you look at 30-minute averages, we're measuring 5 micrograms per meter cube. What that means is it's a concentration which is equivalent to average city in Europe. So it's very high concentrations reaching the high Himalayas. And again, this data is also available at the aerosol website. And where is all this black carbon coming from? A colleague of mine, he just published this paper very recently. We divided the, because this was showing a very distinct seasonal trend, and April is when biomass burning is very prevalent in the region. We looked at forest fires, and the colleagues looked at, they divided the region into 3 boxes, and then this is a MODIS image of fires. And they counted all the fires, and then took back trajectories and looked at where the back trajectories went over the fires, and 56% of the polluted days back trajectories went over the fires. If you look at back carbon on an annual basis here, 2011 there was a significant decrease compared to other years. And then if you look at whereas ozone didn't really show that big of a drop. And if you look at the precip over these boxes, there's a significant amount of rain compared to other years, and less fires during that year, especially fires over southern Himalayas, and then the India box that's shown here. So basically, there was 60% reduction of fires in southern Himalayas in 2011 compared to 2010, showing reductions in black carbon, and then the rainfall was also very high. Again, this is very qualitative analysis looking at satellite and back trajectories. Towards the end, I'll show you model results that try to link emissions with receptor sites more on a physical basis. So if it is biomass, where's all the other pollution coming from? And EVK2CNR with ISS, Potsdam, and ICIMOD, we started a project called SASCAT that Ornika just talked about, looking at pollution in urban cities. And our interest is to try to then connect urban with rural sites and look at source-receptor relationship. So we established a station in the Kathmandu Valley. It's right in the heart of the city, in the 6th floor. And then you can see the background city from the sampling station, and we have similar equipment as in Pyramid. So here is Kathmandu measurement site is in a valley. This is where our Pyramid station is. If you look at the nautical distance, 153 kilometers. And then there's a vertical difference of 3,800 meters. And we have similar parameters that we measure. Paknajol is basically the name of the street that the station is in. We have similar measurements, and with most of the time similar instruments, so it's easy to compare the two data set, which I'll show. SASCAT just started. We were a bit late on the project, but we have data from end of January, continuing till now, whereas Pyramid, we have data from 2006. And here's the list of all the measurements that we're making at both stations. So let's look at some results, and these are fresh off the press, so to speak. It's probably the first time we're showing this here in a public group. So if you look at, this is ozone. Both Kathmandu, Paknajol is showing in blue, and Pyramid data is shown in red. And for a secondary pollutant like ozone, very similar seasonal trend. The top graph is showing daily averages, and then the bottom graph is just showing the maximum value each day. And there are times when, if you look at the Paknajol site, the ozone values are higher because of urban precursor gases are higher. But then if you look at the daily averages, because of high radiation, ozone is higher at Pyramid, just based on radiation and photochemistry. What about black carbon? Similar instruments. Again, first let's look at the magnitude. I mentioned again the black carbon at Pyramid, 5 micrograms is still high. Look at Kathmandu, it's 25. It's still, both places are very high. In terms of seasonality, doesn't show a nice picture like ozone, but then there are some correlations where certain peaks are correlated. There are some events where both show peaks that are elevated. Again, the top graph is daily averages, and the bottom graph is maximum values. During the summer monsoon months, when it's raining every day substantially, the values on both sides decrease significantly compared to the pre-monsoon period. Okay. Just another data for fine mode and coarse mode particles reaching Pyramid and Paknajol. And again, shows similar trend as black carbon being both aerosol particles here. But again, shows you how difficult it is to maintain observations that run for a long period, and not just take data, but you have to take reliable, good quality data. So there are two issues, when you're trying to take measurements at remote sites. And for this particular graph that I'm showing, we're having problems in Kathmandu and not in Pyramid. But again, there are still problems in Kathmandu as well with load shedding and power problems. What about daily variation? If you look at Kathmandu for black carbon, you see the classic peak, early morning peak around 8 a.m., and then another peak in the evening looking at transport and residential. Whereas if you look at black carbon in NCOP, there's only an evening peak suggesting flow from the valley bottom up to the Pyramid. Surface ozone, again, in Kathmandu shows a very classic peak in the midday with high radiation, whereas if you look at ozone, it's rather flat. You see a slight peak here, but if you look at the number, it's just 47, 48 ppb, so it's rather flat compared to the urban side. And again, the particles also show similar bimodal peak in Kathmandu, whereas single peak in the evening in Pyramid. Again, these data are very preliminary, and we're working on this to try to analyze it more and explain the behavior in more detail, and we'll have a paper out soon. Another activity EVK2CNR is doing in Nepal and is the modeling aspect, trying to look at the air pollution issues more locally, and we are running these models in Kathmandu. So if you look at the least developed country, we are one of the poorest. Trying to run modeling studies where there's 18 hours of power cuts is a challenge, and part of the activity of EVK2CNR is to also build capacity and do engage local scientists. So we're running this model in Kathmandu, so it's not as high-tech as some of the modeling work we've seen in the morning, but still is a start, and we're focusing mostly on the Himalayas and urban issues. So the results I'm showing you is a tracer version of, it's 54 kilometers. We use the standard MET models popular elsewhere, WRF, RAMS, MM5. This model was developed at University of Iowa with Professor Greg Carmichael and has been used quite extensively in Asia. So how does the model do? In all these graphs here, the observations are in red, and the model products are in blue. And the model here is not like the climate model that we've heard in the morning. The integration time step is 5 minutes. And I'm running from one whole year, starting from January to end of December, trying to look at the whole seasonality. And if you remember the observations, the seasonality repeats quite well. So if you look at 1 year, you can see what the skill of the model is. And again, as mentioned before, you can make the models look very good. And I didn't want to do that to show that, hey, the model's doing a great job. I just wanted to put it out there that in areas such as the Himalayas, what is the model skill currently? And of course, there's more room to improve. So if you look at the results here in all of these, I mean, the seasonality is captured, but if you look at on a particular day or a particular hour, there's a lot more that needs to be done. And again, this is 54 kilometers, and if you remember the location where the pyramid is, it's very difficult to model that at that coarse resolution. I have done higher resolution modeling, and I didn't show the data, but at the outset, just by going high resolution on the horizontal doesn't necessarily improve prediction. I mean, you want to think about vertical as well as other physics that are involved in that. In terms of black carbon, how does the model do? At first it looks, okay, again, the observations are in red. This is data from the pyramid, and the blue is model. At first, if you look at, it's all over the place. The seasonality doesn't match. But if you look at black carbon modeling, most of the models that are out there usually underpredict observations, whereas our model here on a regional is overpredicting during the summer monsoon. And we are on the same scale. I mean, you're not on log-log scale or a factor of 10 higher, as you see in most of the models. We have some ideas about how to improve, and one of them is we don't have seasonal emissions for black carbon, and we all know that black carbon is, the emission pattern is highly dependent on the season. Also, there's uncertainties related to deposition because of aging. Black carbon at the outset is hydrophobic, becomes hydrophilic. How do you deposit wet deposition? Issues like that. And also, we need to go higher grid scale. What about ozone? Here the model does fairly well, but then again, if you look at it's just 1 month of modeling. And to go high resolution, and again, the scales are slightly different. I don't want to mislead here, but it's capturing the synoptic variability. To go high resolution, sure, you can run the model, but then we need higher resolution emissions. And not just high resolution emissions, VOCs, the speciated VOCs that are necessary to run ozone modeling is non-existent over Himalayas. And that's one thing we will be working on in the future. This is aerosol optical depth. We talk about high aerosols over Himalayas. Here, this is data from sun photometer from the NASA, and again, observations are in red. And despite overprediction of the model, we underpredict AOD during monsoon. And keep in mind that all the observations at the surface show high values during pre-monsoon, whereas observations from aerosol optical depth show high values during summer or monsoon. So the rains may wash out with what we're measuring, but if you look at the column, there's still a lot of elevated aerosols, even higher. So this 1,000 is actually 6,000, so it's the AGL height. So above the Himalayas, there's still high level of pollution going during the summer monsoon. And again, this is model world, and we need to calibrate this. The problem with monsoon is the satellites don't do a good job during monsoon because they can't see through the clouds, and we cannot measure, we can only measure in the surface. So, I mean, we need to think about how do we look at observations during this time period. Again, where are these pollutants coming from? And I mentioned earlier the qualitative analysis. This graph here, we took emissions from Finn model looking at MODIS fires and generating emissions. And so the blue line here shows that the contribution of biomass particles only from biomass burning. So the peaks are captured by biomass, but the rest of the time is anthropogenic. Where's all the stuff coming from? It was mentioned earlier, what burns nearby has the greatest impact. Here we're seeing most of the emissions coming from Nepal and India, the most closest two places. Again, the sectoral distribution was talked about earlier in the emissions talk. Black carbon has a different emissions coming from biomass, residential versus organic carbon and sulfate. So how do we reduce this and still have impact on the climate? And with that, I'd like to end my talk. Here's a beautiful picture of the pyramid at nighttime, and I'll take questions after the next talk. Thanks.
Thank you, Bhupesh. So, Professor Claudio Smiraglia. Indeed, we will have questions at the end.
Don't worry, nothing serious. It's a touch of flu, even strong, but I hope you will excuse me if I sometime have to stop my talk for coughing. Anyway, well, I think that we have already had many interesting suggestions by the preceding speakers. For instance, I have very much appreciated the talk by the Chinese colleague about the fact that we have to pay attention to the use of remote sensing, and we have to use also, again, the field work. And I believe really that we are gaining many information about the complexity of a glacial system. We are coping with a huge mountain range from Tian Shan, Kunlun, Karakoram, Himalaya, Wangduan, and so on, with very, very different climatic situation. And, of course, very different response of the cryosphere. For instance, we have until now, we have to speak about one of the most important drivers of the evolution of glacier in that regions. I mean the debris cover. That is very important, is a crucial point in every investigation about the dynamics of the cryosphere of this region. Anyway, in my speak, I'd like to give you some lines of the evolution of the recent work and results in the framework of the EVK2 CNR committee. I will give you some information about work realized with many other colleagues from Italy, from Nepal, from Germany, and so on. My speech will follow a logic line. First, general and global view, and then a more specific analysis of significant sample points. But first of all, I have to to recall to me, but also to the other friends, that in Italy we have a very long tradition of research in that region, especially through the person of Professor Alito Desio, who was one of the first explorers and climbers and researcher about the cryosphere of Karakorum. And if you see this picture, it's a famous picture taken by Alito Desio in 1953 of the Cutia Glacier. It's one of the first indication of another of the problematic topics of Karakorum range, the Sargent Glacier. And the Cutia was really one of the first indication published, if I well remember, on one of the first issue of the Journal of Glaciology. Anyway, very briefly, from that moment, half of the last century, we began to get a lot of information, of data about glacier, mainly of Karakorum, especially about topography, cartography, geophysical investigation. I have to stress that in that period was realized the first measurements of the thickness of the Himalayan glacier, the Baltoro, in the place of Concordia Circus. It was, for that time, really a very important result. And then the Sarge Glacier, the meteorological condition, and of course the field measurement. From that moment, there was a sequence of many field missions and also of remote sensing analysis about the extension of glacier, the variability of snow extent, and mainly of the debris coverage, supraglacial cover. Field investigation, of course, in the framework of many scientific and logistic and political, I say, projects. There is another thing that I find interesting. All our works have been carried out in two main protected regions. In Karakorum, the Central Karakorum National Park, and in Nepal, the Sagarmatha National Park. And I underline this aspect because I really believe that it's important to get information about the dynamic of the glaciers also from the touristic point of view, of the economic point of view, and so on. First, the analysis of the today situation and most of all of the recent evolution. Of course, EasyMod, for instance, have made many interesting and very good inventories. We only worked on the Karakorum National Park and on Sagarmatha National Park with the aim of comparing the recent evolution. As have you already seen, Karakorum is a quite particular point from the point of view of the glacier evolution. Of course, we just know almost all over the world there is a strong phase of glacier retreat, with a few exceptions. One important is the Karakorum. So we use the normal remote sensing tools and methods, comparing the Landsat, but also other kind of satellite imaging, and between the beginning of our century and the last years. And we evaluated the evolution of the surface area. I repeat, surface area. When we speak and talk about glacier evolution and variation, we have to be very, very clear. We have many possibilities of using the geometry characteristics of the glacier. First, the length variation, the terminus variation, but also the thickness variation and also the surface area variation. We are talking only about the area variation. From this point of view, the variation of Karakorum glaciers into the Central Karakorum National Park is not so evident. It's quite stable, the situation. You can see the table. We have basically no, sorry, okay, no strong differences between the 2001 and 2010. So from that point of view, thinking about the area variation, the situation is stable. Now, it doesn't mean that almost everywhere we find stable glacier. We are saying that, broadly speaking, there is no variation. So it is interesting observe this kind of variation or not variation. We have between 2001 and 2005 some glaciers advancing. You see, this is a famous point, its focal point is the Panma region that starting from the end of the 80s was already studied by a Canadian colleagues, very, very known, Ken Hewitt. And you see this tributary, after 10 years, had an evident advanced phase and jumped down the main trunk of the glacier valley. In this case, we have a really small increase of surface area. In this second situation, another advanced phase, but without increase of area. So, I repeat, we have to be very clear when we are speaking about glacier variation. I like very much these images. It's a very small glacier close to the region I described before, the Panma Glacier. From the beginning of our century to 2 years ago, you can see the morphological evolution. First, the glaciers becomes to grow in its terminus. Then there is a movement towards valley, and then an increase of the terminus with a almost total fragmentation of the last part of the glacier. There is a network of crevasses that is impossible to pass over. And then the snow we have seen before. Snow is important because it's the food of our glacier. So we have to observe and describe the variation of the alimentation of the upper basin. We have used the MODIS data, the normal MODIS data. We have seen that, yes, there is a strong interannual variability of snow cover, and there is a quite slight increasing of the surface area. But in this case, we have no information about the thickness of the snow cover, but only of the areal distribution. And then, very, very important, the evolution of the debris cover. Because, almost the glacier of Himalaya and Karakorum, but also in Tian Shan, in Pamir, and so on, have a broad and large debris cover in their ablation area. It's important from the point of view of the evolution because the debris cover has a terrible effect in changing the interaction between the ice and the atmosphere, and changing the energy balance. If we have an increasing, mainly from the thickness point of view, of the debris cover, we will have a reduction of the ablation. If we have only a rare, sparse debris cover, mainly with a thin layer or fine debris, we have an increasing of ablation. And this is the important point of the black carbon. This is very, very, very fine material. So we have observed that there is surely an increase of the debris cover in the lower, but also in the medium part of the glacier. And then, jumping into the local point, the analysis of the Baltoro Glacier. Baltoro is a huge glacier. You can walk almost 1 week without observe glacier anywhere on the Baltoro, 62 kilometers length. But it's really a icon of the glacier of that region. So we have performed, we have carried out a lot of work over there to get information about the present, the current dynamics and evolution. First, the debris cover. So we carried out a map of the debris thickness by using field works, but also remote sensing analysis. Sorry. Then, important, the thermal resistance or diffusivity to obtain data for model the ablation or the variation of the thickness of the glacier. And we have, here you have a map on if only a limited period of the ablation of this glacier. And then the Sarging Glacier. We could spend a lot of time talking about the Sarging Glacier, but I remember only a few years ago, one total issue of the Journal of Glaciology have been devoted to this kind of problem. Because in the complexity of the situation in Karakorum and in Himalaya, of course, we have also glaciers that almost suddenly had an increase of their thickness, I mean many tens of meters, and then run very, very fast towards valley. We have studied one small sample, Lidigo Glacier, that in the 70s of the last century, yes, was where is the arrows? Okay, here. Was about 3 kilometers, oh, yes, far from the Baltoro border. Now is just, is touched the border. It was a very, very sudden increase of velocity, of thickness, and of length. So, you have to run. Another example for Himalaya. Himalaya, we have made, of course, some analysis of through remote sensing and studying historical cartography. And of course, there is a reduction of surface area, but the dimension is not so high as we could expect. No? We see less than 20%. I repeat, only in the national park. And then some work, field work on another topic of our research, the Changri Nup Glacier, where we installed also automatic weather station to get information about the weather and climatic condition, and to model through the normal degree day model function the evolution. So, to conclude, last summer we had the last, but I don't hope not the last definitively, mission on the field, and the attempt was to get information about a topic on which we have only a few data, the real alimentation at the very, very upper basin. So we climbed, or better, my collaborator climbed, but also Agostino, the upper cirque of the Gasherbrum to get information through the normal snow pits of the thickness of snow, because it's important to have real information collected on the field to compare with the data coming from the remote sensing analysis. And for the first time after the measurement of the 1954 by Enrico Desio, we were able to measure the thickness of the Baltoro in the Concordia area, and it's very important, the thickness, and almost 800 meters. So, to conclude, I like to report this sentence by two colleagues in the 1975. Information on comprehensive glacial survey is extremely scanty, and the account of occasional travelers and mountaineers over the year have little reliability. Maps are also misleading in their lack of distinctive indication for perennial snow and glacier cover. So we have to ask, is the description of our overall knowledge of Himalayan glacier still pertinent today? I don't think so. We have collected a lot of useful data. We have made many work, but it must be clear that we need a greater effort to all the cryosphere science if we want to really help humanity to cope with the present environmental challenges. Thank you very much.
Thank you. So we have a little time for discussion, not much. Okay, and then I please stay there, and also I call the other speakers to come here if there are questions. While you think about questions, I just make a comment to this session, but to all sessions. We have seen a lot of data. Data are crucial, but now I also want to make the point from the point of view of a program such as GEO, the Group on Earth Observations, which wants to build GEOS, the Global Earth Observation System of Systems, this is a huge international group, which includes 90 governments and more than 60 international organizations. And the basic idea is open access data, is open data. Data are very hard to collect, but it's also very important in order to use them, that they become publicly available on appropriate websites. This is a delicate point, but it is a crucial point. Estimates say that 90% of the data which have been collected with public money are in drawers, are not available to anybody. This is a bad situation and should be solved. Given this, I hope there are questions. Okay, I ask one question then. We have learned that glaciers are retreating, which is known, in fact. And we have seen many different views and occasions of that. How can we use this information? How can we use this information for planning future use of water resources, adaptation, and so on? Is there an activity along these lines?
It's quite very difficult. When I talk about the glacial changes in the third pole, even including the Himalaya, Karakoram, and also Tian Shan, Altai, most data or result are just copied from the publication from the paper. Only I'm saying is for the second glacial inventory in China, it will be released. In that case, the people can use it. But majority result, like for the Himalaya, that's very completed, updated review papers just published in Science. We probably can use the data, but that's only from the forum paper. But you mentioned the geos, that's very good, because my friend also working in this is UN organization belongs to UNESCO, so that's no problem. He is also trying to put all of those cross-ferric scientists together, share the data. But the point is, we discussed many times for the cross-fair, especially the mass balance, the different standard, because different place, different standard. And also, a couple of organizations that try to reorganize this, like the WMO is going to have a project named cross-fair late, which means they are going to standardize the glacial mass balance, slow measurements, as well as permafrost, sea and lake ice, and even the river ice. So at first they said, oh, you Chinese people or you Asian people just did a good job. At least you have lots of money and start observe. So let's say Asian cry late. Let's start it. So we are going to discuss in the next December, just in 2 weeks. So we'll have this workshop. So we want to, like the pioneer, to understand, because WMO, they have a really good standard, like the Global Atmospheric Watch. Those stations, they have the same standards. So in that case, the data can be shared and the data quality can be controlled. So that's my whole thing.
I just want to add on that one of the reasons for ICIMO to take an initiative in establishing new stations is that we want to set an example in openness among the member countries in the ICIMO region. For the field campaign we already had this spring, we're very much dedicated to providing the data to the public after it's gone through, of course, all the quality controls. Thank you.
And
If I can add, Mr. Chairman, a comment. Oh, sorry. Well, I have said before, but also the other colleague, but all of us know very well, that there is no uniformity in the evolution of glacier in this part of the cryosphere. I like to stress a thing, especially in Karakoram, there are many glaciers stable or even advancing, measured. They are data. We have no possibility of discussion. The problem is in the diffusion of this kind of data, because I saw many times that, especially when we have discussed, not in scientific concepts, but in divulgation and so on, that there are people who say, that one glacier is growing, so all the construction of the global warming is not real. We have to be very careful and always say, yes, but I'm talking about this kind of area and this kind of glacier, and I have to wonder to myself why there is this exception, this difference respect to the other normal situation.
Thank you very much. I think you have answered my comment, but the question was whether somebody is using the information on the retreat of the glaciers for developing adaptation strategies for water resources.
Actually, after our glacier inventory, actually you can calculate because you depend on the glacial length and also the glacial areas. You can calculate the volume and even the volume change. But those are the still calculation, not the real in-situ observation. But in-situ observation also very difficult because you cannot do one by one for the radar measurements for the volume. But still, we just start another new project. Means we are going to assess or use both the in-situ observations, assess the volume of glacier. So first we have to know how many volume we have. And second, we are going to do the modeling for the glacial change in response to the climate change for this modeling, and we predict in the future how many water resources will be released, and in which time point it's going to increase and going to down. So that's our new project start in our lab. Because in China, mostly when you study the glacier, there's only two institutes. One is our institute of, but both under the CAS. So we understand that. But every time, I mean, you can give the numbers, but who believes the numbers? This number is reasonable or not reasonable? So every time when you close to the nature, then you give the real more close to truth.
Okay. If there are other questions, otherwise we can close this session. Oh, sorry, Gary. There is still time. Not really. It's from your.
Okay. I have a rather technical question. Can you said that the GRACE results are overestimating or they are not good? So I provocatively say that the GRACE is still, and it's going to be in future, the best we can get. We just have a problem to extract the glacier signal from it. And I have 3 very prominent agencies represented here, all very, very active. Academy of Science, ICIMOT and Everest K2. Have you ever thought to improve the methods to extract the GRACE, from the GRACE signals, the glacier portion, which means we have a very, very complex isostatic pattern in the Himalayas. We would need to have a lot more very precise and long records of GPS measurements on many different places. We would need to know more about the hydrology, about the seasonal hydrology, the seasonal snow cover. If we could know that by better measurements on that, we could easier extract and much better extract what we need for a signal from the glaciers, from the beautiful, I still think beautiful GRACE data.
That's great. At least currently, when they published this paper, I just wrote to the author. I said, look, you made mistakes because you just calculate, use GRACE data, calculate the water balance, not the glacial mass balance. They said, well, we just try, also use climate modeling. We just also calculate the water balance, but it's huge errors. I said, look, when you calculate the water balance, they still use the reanalysis data, but reanalysis data in the Himalaya regions, it's not very applicable.
Sorry, we know that was not a very good result, and
That's
it was
right.
actually recalculated for the Gardner et al. Paper. It's a total recalculation with
That's
new
right.
model approaches. But do you plan to make measurements on isostatic movements, on hydrology, on snow cover, on a seasonal basis, which would allow us to extract much better glacier results from the GRACE?
Yeah,
so
that's a good idea.
it's addressing all 3 institutions represented up there. Not just going out measuring glaciers, which will always be very, very incomplete because they are so complicated, they are so dangerous, they are so high we cannot go along that line, although we all like walking up on glaciers, but that's not the way to go in order to know what the Himalayans are doing.
Definitely, at least for the in-situ observations, we can collaborate or even provide the data for validation of this GRACE data, like separated, as you said, the slow water hydrology as well as glacier.
To be honest, I'm an atmospheric scientist from ICIMOD, so I don't quite know all the details of what my colleagues are doing, but I can forward the question on to my colleagues.
I'm an atmospheric scientist too, and I have on my right the most prominent glacial scientist.
You should hire geophysicists.
Yes, I think that suggestion of Georg is very, very important. I don't know if in the framework of E2, K2, SCNR, it will the possibility, I hope really, no? But I'd like to add another suggestion about the preceding question of our chairman, about how glacier research can help I mean, all the evolution of a population. I think that we have to try to have best contact and links between field workers, modelers, hydrologists, and so on. You know very well that we are talking about a system of enormous complexity, and sometimes the relationships between among the different kind of researchers are not so simple. I'm getting older and older. I feel that that is the way to follow, to get more information for the utility of the mankind.
I just have a comment regarding the remote sensing. It's not related to glaciers, but we all know, even for atmospheric sciences, satellites have a lot of problems. So I think one way forward when we talk about cryosphere regions in mountain areas is to better improve remote sensing technology over those areas.
Okay, thank you very much, and let's go to the next session.
And I'd sort of encourage people to stand up and move around, because we've had, you know, the three polls, you could say, at this point, and now we're moving into a session that is all of these other cryosphere regions. There are millions of people who live in them. They're still important. And so we're going to have some presentations now talking about the Alps, the Andes, you know, I'm standing here wearing a maple leaf. I live in Vermont part of the time, very, very dependent on cryosphere at this point for its tourism industry. So there are a lot of places that are relying on the maintenance of snow and ice at this point in time. So we'll move first to Georg. I will let people know that they will take the coffee away at 5. And so if you need a caffeine boost, you should go before then. And then we will be ending at 5:30 or shortly thereafter. The negotiations, from what I have heard, went through about 4 a.m. last night. And so the Swedish and Bhutanese heads of delegation who were going to come and close us have asked if they could sleep instead. And so we will have some sort of concluding statements, but we will certainly not go beyond the 5:45 and probably end a little bit earlier than that. So.
So it's getting cozy again. It reminds me to yesterday. Actually, I love it like this. I had the task to report about East African highland glaciers or mountain glaciers and have a kind of a detour into the Alps. So I just choose the freedom to slightly change the title, and I go rather into a low latitude perspective than to East Africa only, and I will follow Pam's wish to talk about the Alps afterward. I also thought I do an excursion out of this foggy atmosphere of COP19 into the bright, thin air of the high mountains where light is much clearer. And it is actually a little bit away from these technical issues we have to address here. And I take the risk to miss my mission here. We have this part of showing how bad the whole thing, the whole story is, how big the changes are, and that's something which is really important. But on the other side, science can also be fun, and that is something I like sometimes, to really escape from all these not so nice things we have to tell the audience and the society all the time. So let me start with just counting what glaciers are, what shrinking glaciers are. They contribute to sea level rise. They have an impact on regional water availability. They can cause hazards. They can tell us about the drivers, and then it becomes interesting. Are these shrinkages due to internal variability? To which extent? Are they due to global warming? Are there other drivers behind that? And there is actually a chapter out in the IPCC report for the very first time, it is the chapter 10, that deals with detection and attribution. And detection is just demonstrating that something has changed beyond the statistical noise. So beyond the internal variability. It is detected that the changes observed are following a trend, so to say. And attribution then comes in order to say, these are the reasons. We know the drivers. The drivers are this and that and that. And that comes back to what I said before. What are the drivers? On a global perspective, the chapter 10 concluded about glaciers that glaciers are melting and that anthropogenic influences are likely to have contributed to the retreat of glaciers since the 1960s. And then they had also a very nice sentence that we glaciologists know a lot about glaciers. I love this sentence, although I was not participating in writing it. Now, if I repeat a figure which I have shown you already, then it comes to this tiny little dot here if we talk about the low latitude glaciers. This is mainly the glaciers between southern Bolivia and up to Venezuela. It is the three mountain regions in East Africa, and it is the Puncak Jaya in Irian Jaya, so it is only ice patches left. But what can they tell us? They do not contribute to sea level. I mean, nobody cares about them. They do contribute quite a lot here in the Andes to the regional water supply. They do not do anything to water supply here or here. But what can they tell us? We know they are shrinking. They are shrinking very fast, and most of them are very small glaciers, particularly if you go away from the Andes. There are some very big ones in the Andes, and they will still remain for a very long time, whatever the climate does. But some are very small, and actually Lewis Glacier on Mount Kenya is just about to disappear. Last time my colleagues have been there, they reported about a big hole or a big rock outcrop, so it has started disintegrating. And it is not so difficult to say it is because there are warmer temperatures affecting these tiny little glaciers. But if we have a closer look, then these glaciers here, as named on different sites, they all are somehow in areas where we have highly interesting modes of circulation patterns. It's the El Niño Southern Oscillation, which affects basically East Africa, Irian Jaya, the Cordillera Blanca more than anything else. We have the North Atlantic Oscillation where the Alps and the Scandinavian Alps are in. We have the Asian monsoon. And if we then look into cross sections here and here, we may be able to learn a lot about these modes and how these modes have changed or are going to change within the climate change of the entire system. But this is work in progress, and I will just give you an insight into this work in progress. First of all, we have to define the sensitivity of different glaciers. And this is just two glaciers in the Alps over the time of an year. Here is their sensitivity from October to September on temperature, and here it is on precipitation. And if you do similar things all over the Alps, you see if you only let them be sensitive to temperature, then this is the color scheme, or this is the color distribution. And if you do something only with precipitation, then you get something else. So they compensate each other, or somehow complement each other. I do not go deeper into that. We do sensitivity studies. If we then have these sensitivity studies, then we can look into how they correlate, for instance, to a North Atlantic Oscillation Index. And it comes out that the glaciers in southern Norway, or southern Norway, they are they have quite high correlations, and this is due to precipitation. It is not due to temperature. Whereas in the north, it is due to temperature. They have a negative correlation with NAO. In the Alps, temperature and precipitation correlation compensate each other, and there is not really much you can get out of that if you look to the mass balance of a glacier. And it is the mass balance. It's not surface area changes, it's not length changes, because then it becomes much more complex. It is the mass balance sensitivity. If we look into the entire chain of the Andes, then we see kind of a color scheme which actually has a part which, in the first plot, shows that we are here in the subtropical easterlies. We are here in the westerlies. So there is different sensitivities. If we go deeper, then we see that those glaciers here, the yellow ones, they are sensitive to probably to an El Nino. We do not know exactly what this tells us. It's just a statistical analysis of different EOFs, and it might be that here we have a higher impact if the ENSO changes than we have here, for instance. With this, we don't even know what it is. It can be something. We still have to look into what the different drivers or the different sensitivities are. But this is a very, very strong tool we can further develop. And if you see, there is kind of a change from here, from the westerlies to the easterlies of the subtropics into the tropics. Let me go to Kilimanjaro. Kilimanjaro is a very high, alone-standing mountain. It's almost ideal for modeling. It is a Gaussian-shaped mountain standing totally alone. It's like a mast with a thermometer on top, but it's not a thermometer. It is a climate meter. It's a bunch of ice. And this bunch of ice has developed from 1912 to 2011 the way you see here. It has just shrunk. It has become very small. But if you have a closer look, this is not a normal glacier. It's not a normal setting of glaciers. It is dominated by vertical walls. And these vertical walls are just contrasting very highly with the very dark ash surfaces. Most of them are rather plain. So the entire plateau on the surface is plain. It's not sloped. The slopes start here on the edge. And we have a few glaciers going down. We had many of those glaciers going down. We still have few glaciers going down. But what is this all about? If we have normal glaciers, this to the left is a glacier, this is a ice cap or an ice sheet or whatever. If you change the mass balance, and so you change the volume or the thickness of the two classical ice bodies, then you change the surface area. And what you have seen before is just surface area changes, nothing else. Doesn't say anything about the thickness. So this is normal. And usually if you change the thickness, you change the surface area of a normal slope glacier in the front area, but not in the summit area. And here you do it on both sides. On Kilimanjaro, we have those two type of glaciers. We have the plateau glaciers. If you change the thickness of that, you won't change the surface area. So you can make them down to 0, and then all of a sudden they are gone. So there is no gradual change in surface area. So if you have a gradual change in surface area, it can only be due to the retreat of the cliffs. On the other side, we observe something on Kilimanjaro which is not like this, having the loss in the lower parts due to higher temperatures or higher melting conditions. That may play a role because we have mass or surface area loss here, but also in the summit area. And this is just a sign of drying out. Now, we do a lot of studies, or did a lot of studies along these ice cliffs, a lot of micrometeorological studies here. We even went up to do turbulent flux measurements in order to fulfill this balance of energy and of mass fluxes, and in order to see what the different agents do to this wall. And we found out that during the shady period, they are on this almost exactly on the equator, 3 degrees south, and they look either north or south. And so during the shady period, there is a slight retreat of this wall. This is the wall retreat. And then it increases during the sunny period, and then it goes back. What this says is, and we have to take in mind that the temperatures here are usually -7, -5. They never reach, or almost never reach, 0 degrees. But if you have a strong sunshine and no wind, then you can melt even down to -12 degrees. Just no wind, just switch off the wind. And wind is not a really agent up there. We have windy days, but usually you can really melt every day, even if the temperatures are below 0. And this is the melt retreat. And then it melt plus sublimation, because it's very dry. And then it turns into sublimation only. And then again to melt. And we have observed that over many years, and it's very constant. It's each time about 90 centimeters on the southern side, 90 centimeters on the north side. So every season takes away almost a meter from each side, and so they have to be gone. And there is nothing on warming or so. It's not even drying. It's just the Holocene climate, which was interrupted occasionally every couple of 100 years by a piling up of snow on the entire surface. So you have to remove those vertical walls, just fill it up with snow. And that's easily done if you just have heavy snowfalls twice a year. We have experienced one over the last 10 years. That was not enough, but if you have it over 20, 30 years, then you pile up the glacier as it was, 100% glaciated the plateau. So the vanishing of the plateau ice is just due to a very normal process of very slow adaptation to conditions which are most probably the normal Holocene conditions. And the remnants of the ice, or the ice we have up there, are remnants from a series of snowfall events, or a phase of about 30 years, 20 to 30 years of heavy snowfall events around in the early 1800. Now let me have a look with you on the Slope Glacier, on one of the remnants of the Slope Glaciers. We know there is a moraine of 1880, and that if you have a moraine, you can always say that was kind of a steady state or close to steady state situation. So you can somehow estimate the climate conditions which, as an average, have governed this glacier. And this is then the model results, and I do not go through everything. We just say this is the average between 2005 and 2008, which we have measured. We have temperature, this is the average temperature, -7 basically. This is the average precipitation here, 500 millimeters or a little bit more. We obviously do not reach the moraine. We are far off that moraine, so we cannot say what the entire 1880 glacier would have as a mass balance. This lowest is the mass balance, but we need to reach a mass balance of 0 in order to get a steady state at this position, at the 1880 position. And we have a few options. We can change the temperature. We can get colder. And this is not just an invented temperature change. This is about the temperature change we have reconstructed from other proxies of that time, 1880 roughly. But we still get not down the glacier. It's still very, very negative if it was at this position. It was not steady state in case it was only temperature. But if we rise the precipitation just a little bit, and there are indications on lake levels and a lot of other things that the precipitation was somewhere 200 millimeters higher than here, roughly 150 millimeters higher than here, then we easily get it down. So it is a pure moisture signal we get there. And the question is, where does this moisture come from? Who governs this moisture? And we have done studies on both sides in the Cordillera Blanca here, where we have glacier mass balance measurements over many years, and we have compared it with the sea surface temperatures out in the Pacific, and we have done something similar with the East African precipitation and looking into the sea surface temperatures of the Indian Ocean. And that is actually a highly interesting thing, which I do not extend here only to this point, that we have run model runs, or we have extracted a model run in order to get this Indian Ocean Zonal Index, which is similar to the North Atlantic Index or whatever, or ENSO indices. This Indian Ocean Zonal Index, if it gets beyond or above this broken line, then this is related to heavy or ongoing and strong precipitation in East Africa. And it is not that much, it doesn't say that much about the amount of precipitation, but look at the frequency. We have here a time period from here to here, where you have almost every couple of years you have one of these indices or these ocean situations in the Indian Ocean that allow for heavy precipitation. And then we have a gap, it becomes very dry here. And then we have only occasional, rather strong signals, but not something which is really keeping a glacier building up. So on Kilimanjaro, you can just build up or let it go. There is no way to have it in a balance. And so we have here a period, and we assume that this was the period when the today's glaciers were built up, and we have here another period, and we know from then on, from 1880 on, they have just retreated. Altogether, we have to look into a rather complex system. So it's the large-scale drivers which cause the mesoscale conditions on the glacier, and we have also to understand, or we then as a result have the microscale processes or the features, the microscale features, as for instance these vertical walls. And that is our chance to model the whole thing. For instance, we can get from global atmospheric or one of these global climate or weather models, we can just drive regional or limited scale models, like here a WRF model, I think that was done on WRF, or doesn't matter, in order to simulate normal or occasional or extreme conditions, cloud conditions, or these pumping conditions of pumping up moisture to the mountain. And this is, for instance, a wet air situation during the wet season, and this is a situation during the dry season. And we see during the dry season, the clouds do not reach the summit. They do not even shed from the sun. So they are exposed during the dry season. Whereas during the wet season, you have a daily kind of convection which really penetrates through this subtropical inversion layer and goes up the mountain and thus causes precipitation. Now, we have then taken the results of this limited area atmospheric model in order to drive a dynamical downscaling model. This is a mass balance model, and we have done this modeling by forcing it from automatic weather station data and by forcing it from the previous greenish model results which I have shown you. And this is for the wet season, and this is for the dry season on Kilimanjaro again. And we are quite happy that this works really very, very well. So we are able to model both the wet season conditions and the dry seasons conditions in a very, very straightforward and also very physically understanding and physically constrained method. This allows us to go really to the physical processes, to go back to the physical processes, to be identified, not just in this approximation way we did on the slope glacier on Kilimanjaro. In the very first study, my colleague Thomas Mölk has done on Zhadang Glacier, which we have learned already about. There is a lot going on there. And they have done exactly this study. And with this figure, I just show you that the modeled values I think in gray match very nicely the measured ones. Whatever you do, there is a lot of different things. So this model chain really works very well. And it's driven by atmospheric models. The outcome in that case is that they had 3 different years. And these 3 different years had a very late monsoon onset in 2009, early monsoon onset in 2010, and a very early onset in 2011. And the impact is very high on the melting at the surface. It's the surface melting. So it is not really temperature changes in terms of global mean temperatures or not even regional temperatures. It is the onset of the monsoon, which may change from year to year. But if that onset gets gradually earlier or later, that has these small and very dry glaciers, we are on very high mountains, very small glaciers, very high glaciers. They tell us a lot of the modes in the surrounding and basically the moisture conditions which change within the entire change of dynamics of the climate system. Just recently we have evaluated data from Glaciar Shayab in the Cordillera Blanca, and this is the vertical distribution of mass balance in 2 years. And you see that in the accumulation area, here we have the positive values, above 5,000 meters. In both years we had accumulation, and this is not very different, it's very similar. But here they spread out, they just partition from each other. So in this year, in the 2006-07, we had much higher ablation rates on the tongue than we had in 2007-2008. But if it had been higher temperatures, so, or whatever, or higher precipitation, the shape had been the same, and there was just a shift, a parallel shift of the whole thing. So if it is temperature or precipitation, you would have to get them apart from each other the same amount here and here, or just lift that up or whatever. So you had to really parallel figures, but they are not parallel. There was something going on the tongue, and we then through these model approaches found out it has to do with the albedo, with the reflectivity on this tongue, and that again has to do with the frequency and the daytime and the temperatures when precipitation events occur, and they occur only suddenly for an hour, half an hour, and then it's gone again. And it depends very much on how much on a dark surface you get of snowfall, at which time of the day you get it, and whether the temperatures are slightly higher or lower. So we have really to look into something which is beyond the average temperature rises or average precipitation. This makes a big difference on the total mass balance. The total mass balance is much more negative here than here. And so we need to look into this. And this is quite, just let me say the last sentence to this one before I go to the Alps. This is something which is so far rather straightforward if we go from the glaciers and try to understand the drivers. But if we now go the way back, the other way around, if we inverse the whole problem and say, we know about the drivers and we would like to know what the glaciers do, then it becomes extremely complicated. We all know this is highly non-linear systems, and you go from an effect to a result, but if you have the result to trace down what the effects are, is much more difficult. So this inverse modeling has just about started, and there are a bunch of young and very, very skilled people out there. I am confident within the next couple of years they will solve these problems or get ways to tell us much more from this perspective. Now, there was one particular thing which was around in the Alps for years, the retreat from the Little Ice Age. So this is the earliest picture ever, or the earliest picture known, the oldest picture known from a glacier. It's Vernackt-Ferner, which dams the runoff of Hintereisferner, Kesselwandferner, Hochjochferner, all quite well-studied glaciers today. Caused a lot of floods, so even during Little Ice Age, that was not paradise. Instead, it was a really dangerous time in the Alps, for instance. Many of these glaciers did these odd things. But then the glaciers started to retreat rather suddenly. That actually was a surging glacier, so it was kind of different thing. But they all started to retreat. And the retreat was in a way that started somewhere. It's different glaciers in the Alps, and this is length variations. We don't have anything about mass before 1950, 1960. So the length variations indicate that all these glaciers got smaller from around 1850 onward. But the winter precipitation, which is one of the loading it is the loading component in the mass balance. Winter precipitation did hardly change around 1850. It got slightly down, but not really. But the temperatures got down, so it became colder. So there was a big question mark. What was going on? The glaciers retreated very strongly, but the climate didn't tell to retreat. They just did. And this is just a normalized way. Sorry, I have still both. I thought I have taken out the first one. It's a normalized length variation of 3 of those glaciers starting in 1850. Not much going on in the precipitation, but a slight temperature decrease. Now, we have 2, 3 different ice or fern cores from the Alps, which is the Colignifetti and the Vierschehorn. And yeah, I do not go into there was a mistake which is in the paper, in the published paper, which I discovered last night. I found it out with Tom Painter. We had a bit of an email contact. So it should be, the broken line should be Colignifetti, the lower one, and the thick line should be Vierschehorn core. They show that around 1850, the content of carbon, of black carbon, increased in these ice cores. So we have an increase in black carbon content. Here we have it going up and then a little bit down and then up again. But compared to before, we had a higher load of black carbon, even in the very, very high summit areas of the Alps. It's not easy to explain how the black carbon get up so high. It combines very nicely or correlates very nicely with the Europe emission bond, that is the source with the emissions in Europe. This is the black line, or the emissions in France, Switzerland, Germany, and Italy, which here are reference to another paper. So the emissions were there, and there is a deposition. That's the short story of a long talk. Now, colleagues back around Tom Painter, they did the following. They said, if we have on the highest summits this amount of carbon load or black carbon load, we must have more on the lower portions, and they must be most effective during the snow melt period. If the bare ice is bare, or if the ice is bare, that is dark enough. If you add a little bit of black carbon, you won't change any much. And so we have decided that we do 3 runs. This is if we have in April, May, and June, just the same amount as measured on Vierschehorn and on Colignifetti. Then we have got this forcing out of that. If we take a 10 times forcing, which is the blue line, then we get a much higher forcing. If we take a 20 time amount of black carbon load throughout these months on the snow surfaces, on the lower parts of the glacier, then we get this amount of forcing. And this forcing was then translated into a temperature anomaly, and with this temperature anomaly, Ben Marzeon has then modeled the mass balance of a series of glaciers, actually all of those glaciers which we had length variations, but Hintereisferne is the interesting one because this is the evaluation period, and this is Rhone Glacier just for an example. And if he goes just with temperature and precipitation, as it was measured, then they become positive, they should advance. It's positive mass balances in both cases. But if he then drives them with this forcing, either from Vierschehorn or Colignifetti or both, then they go down, and that causes this shrinkage of glaciers, mass loss. We have not gone that far to say we can also model the length variation, because that depends so heavily on the topography of the bed. It's very, very difficult to interpret a length variation out of a mass variation. We can just say the sign is the right one. So in order to sum up, small, high elevation glaciers can tell about climate change beyond temperature change, and the black carbon may have caused, and this is just put down as a hypothesis. We cannot prove it. So the models are, or the model input, the input we would need for the very good models, the very sophisticated models, is not available. The models were there, but we have not the input to do that. So as a hypothesis, we can say the black carbon may have caused glacier retreat before the end of the Little Ice Age. And I thank you very much. This is part of my team, just being lost on a glacier.
Well, good afternoon. So well, first of all, I would like to thank the organizing committee for including me in this in this event, and I would like to share with you a new initiative that we just started last month. So, and this is the pollution and the impact on the South American cryosphere, which we were able to find a nice acronym, PSAC, which as many of you know, this is one of the a very important archaeological site in the Sacred Valley in Cusco, Peru. So, okay, so let me see. Let me just, we already have heard a lot of the talks on the cryosphere and the Arctic, in the Asian cryosphere, as well as George has talked about the Alps and Africa. So fortunately, this is the last talk, so I have, well, I guess there's one more. Okay, so there's a lot of things already been talked about, but what I would like so some of the science policy questions that we are going to address are also similar to what's been discussed before, but we are in a very, very early stage of development. And so, as I mentioned, just only starting a month ago, which is essentially, it's an ad hoc, we just, a group of atmospheric scientists get together, and we realized, you know, after looking at what's available, and also I've been working with Pam on the ICCI projects and previously on the methane Blue Ribbon panel, so I'm very interested in looking at the impacts on the cryosphere, and so a group of us just get together and we thought that we should look into the Andes, and the group meaning that I've been doing a lot of work in Mexico and in South America. So so as a result of that, we formed this initiative, and we had a workshop just last month. So let me just talk a little bit about Andes. So Andes is the longest continental mountain range in the world. It's about 7,000 kilometers long, and it's 200 to 700 kilometers wide. Actually, most of the range is about 200, but in the area of Bolivia, it's a little wider. And the average height is about 4,000 meters. And here, this is the highest peak, which is in Aconcagua in Argentina, which is almost 700 meters high. And this one is, so the Andes extend from north to south through 7, I guess I show here a map of the South America, so it's extend all the way from across 7 South American countries: Argentina, Bolivia, Chile, Colombia, Ecuador, Peru, and Venezuela. And so this is the composite satellite images, okay? So it's the Andes, this range has very complex topography and covering several climate zones and has diversity of ecosystems and communities. So a variety of sources emitted along the Andes and with varied cultural and behavioral aspects. So now the workshop, the objective of the workshop, as the working title is just Workshop on Black Carbon in the Andes, but we are looking more than just black carbon. We look at all the other pollutants, co-pollutants, and so this was organized hosted by my colleagues at the University of Chile in Santiago, Chile. The objective is to discuss the key sources and impacts of black carbon and co-pollutant emission in the Andean regions with the aim to design research activities to close the knowledge gaps, as well as to address the mitigation measure for near-term climate protection and air quality improvement. So the product is to produce a white paper addressing the topics on emission. What do we know about the key sources of black carbon and co-pollutants that influence the Andean cryosphere? How can we adapt existing inventories? And what about future emission scenarios? The observational sites, what are the key observational sites and instrument that are needed to address the origin and the fate of black carbon and co-pollutants along the Andes. And modeling what are the key atmospheric processes needed for modeling black carbon and co-pollutants, what are the potential impacts of black carbon emission and co-pollutants on the Andean cryosphere. And we also want to address the policy implication, what mitigation measures have been proposed and all implemented to address the impact of black carbon and co-pollutants on the Andean cryosphere. So it's similar to what's already been described by others, but let me, okay, ups. Okay, so here the workshop includes representatives, I would say, from all 7 countries surrounding the Andes, as well as Brazil, which is one of the key emitters. We also, it's interdisciplinary. We have atmospheric scientists, we have policy experts, we have glaciologists. So we have an interdisciplinary group, about 30 people get together. Okay, so we discussed the emission. There are many sources, and actually, let me just also mention that. So we form working groups, and we have assigned coordinating authors and contributing authors, so that what we would like to do is to come up with a white paper, hopefully by summer of next year, so that we could use that white paper as a means of, well, first to, it's also to understand what's happening, as I mentioned, to learn, to improve our understanding, but as well as also to use it to solicit, or maybe I should say that to seek financial support, so that we can, that would enable us to start collecting data and to design mitigation strategies, or I would say measures, okay? Okay, so the emission, there are many sources of emission. The main one are wildfire and biomass burning, and some are natural and some are and the anthropogenic, especially from agriculture burning. There is also urban emission, very important. One are the mobile sources, and other sources, South America has many volcanoes, so that's another thing that we have to consider. We need measurement to improve emission inventory for South America, particularly the region surrounding the Andes. So the measurement should be coordinated, and the methodologies and the protocols should be harmonized. And we need to address economic and social, cultural issue in addition to the technology. So this has already been mentioned also by previous speakers. The ultimate goal is to develop an emission inventory with the spatial and temporal distribution. So this one is just to show pictures from my colleagues showing that the smoke, in fact, transported above the Andean mountain, and so that's from Bolivia. Okay, now measurements and monitoring. We need measurements to validate the emission inventories, and also to validate the atmospheric processes, chemical transport, and climate models. And so we discussed the technique that the less expensive and less sophisticated technique are useful for monitoring to establish trends and the statistical correlation between presence of pollutants and receding glaciers and the snow cover. But we would also use more complex instruments for research and special studies in order to understand the processes by which pollutants are deposited on the snowpack and the glaciers. Now, we would link the measurements of pollutants in the Andean region with population health. That's a short-term goal, and look at the water availability and quality, as well as food security. Okay. We set up a standard laboratory, but every country should have its own laboratory. In fact, it would have been, right now, currently, there is only one monitoring station in Bolivia. So it would be very useful for this project that there will be a monitoring station in each country with in situ and remote sensors that can measure properties of black carbon and dust in clouds, as well as cloud-free air. The samples can be taken also by volunteers, which I'll show some picture of the American Climate Science Program after appropriate training or during field campaign that target a specific region and time period. And while we would like to explore a lot of cheap stations with good spatial coverage for monitoring trends and transport, we also would need more sophisticated station in Andes for research. Okay, so these pictures is the station in Bolivia, in Chacaltaya station in Bolivia, which is, as I mentioned, this is from my colleagues, Marcos Andrade, the Universidad Mayor de San Andres. It's the high altitude GO station that was starting operating in 2011. The aerosol properties as well as gas concentration are measured. Observations show a clear sign during biomass burning. And in the long term, they would like to maintain a regional station measuring both gases and aerosol. Okay, okay, let me just go to the next one. So this is another example of work that has been done in the, as I mentioned, that there are very few information, but although there are some measurements that has been done by individual scientists as well as institutions. So this is one of the very extensive work that was done by Francisco Cereceda in Chile, and so they actually look at the pollutant transfer from cities or from Santiago, and so they have apps. Sorry, I guess, okay, here. Okay, they actually set up a lot of monitoring stations along this region, the different region in Chile, which is very thin. Okay, now, and this one is just, so through the study of snow and aerosol sample collected in sampling campaign, longitudinally across the Andes, they expect to evaluate the impact of pollution transport toward the Andes glacial and the influence on the climate change and water reserve in Chile. Okay, this is, so again, now a very innovative sampling collection is done by this, what I mentioned, the American Climate Science Program. And this was shared by my colleague, Carl Schmidt from NCAR. So this is all volunteer citizen science program. The scientists and non-scientists, climate, they participate in the research expedition. And the climate helped the scientists with data collection in the valley and on the mountains. The sampling protocol are designed to be very simple so that they can be completed in the field during challenging conditions. The scientific value is a modest sacrifice in data quality in exchange for a large quantity of data. So they have collected 240 snow samples over the 3-year period. And so the sample actually indicate that there are some higher loads of light absorbing material than the north end of the range. Then this could be sources of the pollution could be urban air pollution, the high concentration of the dirt roads, the nearby mines, agriculture burning, heating and cooking with wood. So here this is an example of how they collect it. So basically the climber, they just collect the snow in bags and then the snow is melted and they immediately filter through quartz fiber filter. And then these are stored in coin holder after filtering, and they have done a lot of work throughout. This is done in Peru. So as a result of this, actually, one of the nice things coming out from the workshop is that now NOAA is very interested in analyzing the filter sample for this group. Okay, now the modeling okay, I'm almost done. To better understand the atmospheric processes, pollutant transfer and deposition in the Andean region, and to produce scenario for decision maker addressing the following. What are the potential impacts of black carbon emission and coal pollutant in the Andean cryosphere? And what are the impacts on the population health and the environment as well as economic costs? And we would like to also evaluate the land use changes and conduct cost-benefit analysis of potential mitigation processes. What is missing in modeling requirement is that there is no South American emission inventory currently available. And the land use, land carbon emission inventory need to also be regional. So the regional scale modeling to allow intra-city collaboration, discussion, and agreement, and sub-regional assessment, differing aerosol aging processes east and west of the Andes, as well as meteorological models and parameters. Now, let me just so the policy, research may provide information with policy implication and decision-making consideration. The source sector emission and priorities and their implication on health and ecosystem are needed to establish a research agenda. And we'll use interdisciplinary research is needed for designing the mitigation measures. The time frame of scientists and policymakers are different. So we need the best available scientific information to promote discussion among the policymakers. And so let me just conclude that the white paper would also address, the focus is on Andes, but we also address urban emission and impacts, shortly climate pollutant, water security, health, as well as land use. And I would not go through the opportunity available, a great opportunity now because of the interest in emission, especially in the urban scale, the water security and new instrument and sites. But the challenges are lack of emission data, limited monitoring station, inadequate human resources in some region, as well as insufficient financial resources. And we also would like to do outreach activities to strengthen human resources via education and capacity building, engage the various stakeholders, government, non-governmental organizations, as well as private sectors, and raise awareness in general public via various media. So let me just show pictures of this is the group of the scientists and policy experts meet together. And thank you very much. Okay.
Okay, Mario.
So thank you very much for the patience to stay here until the end of the day. And I hope that this presentation will be the last but not the least, but I'm not sure of that. So at the end, you can say to me if it's the first or the later. So I want also to thank to AV, K2, CNR to invite me for this opportunity to change my experience with the several much more famous colleagues than me. And I want to speak about another part of the permafrost. This morning we have already listened the most famous and not visible but famous permafrost, so the polar permafrost. But you have to think that there is also mountain permafrost. Mountain permafrost is probably more difficult to find and to detect than the polar one. And I want to speak about this topic in two different regions because are in two different hemispheres, the Alps and the Andes. So, why? Okay. So I wanted to skip the first sentence because we have already listened this morning, but I want to underline the second one. Mountain permafrost has characterized very important, the spatial variability. The spatial variability of permafrost in the mountains is even higher than what you can find in the Arctic. Why? Because we are in the mountains, so there is a rugged morphology. There is a big variability of the topography, of the slope, of the aspects. And this means that solar radiation can change a lot in a very small, at very local scale, but above all, the snow distribution is strongly affected by the wind redistribution, and the wind is affected by the roughness, and the roughness in the mountain is very high. So keep in mind these 2 points for all the presentation, and if you have questions at the end, especially on these 2 topics, I would like to answer. And another important thing on the mountain permafrost is the nature of the lithology. We have a much more variability also on this respect the Arctic. We have a lot of coarse materials. We have rock face, and the rock face is in permafrost, but mainly without ice. So, in some sense, it could be also not frozen, but below zero, and or without ice in any case. And this is another important point, because we can have some measurements, we can have some data about the permafrost distribution, but it's really difficult to have data about the ice in the rock and the ice in the sediments in the Alps. But the ice content is the main thing that can trigger the 3 different points if we put this mountain permafrost in a climatic change scenario like what we are living now. Because if the mountain permafrost change, we can have an increase in the slope instability. We can have changes of water runoff and water circulation below the ground. And last but not least, at least for my field work, are the changes in vegetation and the CO2 fluxes that can be related to the changes with vegetation. So the first point, the ice in the mountain permafrost. Here you can see 2 different kinds of ice. This is pore ice and segregated ice. There are both in this point, but is a normal ice that you can see in a coarse grain material also in the polar environment. But it's really difficult to find this ice or to see this ice in the Alps or in the Andes. This kind of ice, so very thin slice of ice in the fractures, in the joints, in the rock, is much easier to find and to see, especially after a hot summer like 2003, when a lot of rock falls can go down from the rock falls, the rock faces, because the active layer was thickening. So some centimeters of active layer thickness more, and the ice in the joints is partially melted. The strengths along the joints decrease immediately, and the rock slab fall down. So I summarize different kind of slope instability that you can find in the mountains if you have sediments or if you have rock outcrop. So probably the most famous, at least in the European Alps, event that kept the attention of the media was the rock falls that in 2003 affect the Matterhorn south face. But main of the media spoke about permafrost warming, but it was completely wrong. This was an active layer thickening, so just a seasonal phenomena. Permafrost warming means a decadal or century of change, not seasonal. On the other side, you can see a map of an area close to Stelvio National, in the Stelvio National Park, a bit very close to the Switzerland border. in which you can have the active layer thickness in blue and turquoise, and the red dots are where the debris flow started. The debris flow represents one of the more important, in terms of economy, event of instability can be related to the permafrost occurrence. But keep attention that in many cases, those debris flows are triggered during or after, immediately after the snow melting, when the active layer is very thin. This means that if you have permafrost, you can have more possibilities to have a debris flow triggering. It not means that is the water that melts in the active layer that can produce the debris flow. And look, these mountains that is more than 3,400 meters high. In this picture was in 2003, so in the very hot summer. But in 2004, much a normal year, so not so hot, not so warm year, the peak changed completely its landscape because one big landslide, 35 meters deep and more than 1.5 million of cubic meters, fall down in September with a sub-zero temperature. This is not an effect of the seasonal changes, but this is an effect of permafrost warming. The permafrost warming that occurs during the 90s, during 10 years before, or the decade before. And this is another big landslide, Valpola landslide in Upper Valtellina in Italy, in northern Italy. This is the more important natural, unfortunately, disaster that in Italy happens in the last 30 years. More than 20 people killed below this landslide. And the scar where this big rock avalanche of 40 millions of cubic meters fell down is still now characterized by permafrost with quite a lot of ice in the joints, in the fractures. So the permafrost is still there, but the permafrost temperature changed quite a lot because now the permafrost temperature there is just below zero, so 0.2, 0.3 degrees. But 50 years or 40 years so before the landslide, the temperature was probably more lower than minus 1.5. So permafrost temperature is very important to trigger big landslides, deep landslides. So about the water, we have 2 points. So how much water is stored now in the permafrost in the mountains, especially in the Andes, that is in large part in arid areas? How much? Who can reply to this question? Nobody. Because we don't have data. We have some data about the permafrost distribution. We know that there are large portions of the Andes and also the Alps with permafrost, but we don't have any data at all about how much ice there is inside. But this could be an important water resource for the future. Someone said that probably much more important than the glacier in terms of water stored. But I can't believe because it is not true. We don't have data, so it's impossible to say. We can't say with one dot on all the Andes or 6 or 7 dots in the Alps that the ice amount is probably some, I don't know how much. Another important point that in the last 5-6 years, at least in the Alps, is developing is how the water, the groundwater, is changing the aquifers, the circulation, in respect to the climate change, in respect to the permafrost warming and to the thickening of the active layer. There are only, I think, not more than 5 or 6 sites in all the Alps in which there is a monitoring program on this, so not more, and not more than 1 in the Andes. But at least we started to keep in mind that there is this problem, because the problem starts from the people. In some places in the Alps, for other reasons related to the European rules for the water potability, the water that comes from not permafrost areas contain some kind of pollutants that the water that comes from permafrost aquifer doesn't have. And from this European rule, some municipalities started to look where there is the water below the permafrost, just for a European rule. I tried to explain this to the politician for 10 years, and they never listened me. But after the rules, now we can start to work on this topic. So just some images, because we are monitoring the water runoff and the water infiltration in one site in the Alps. And, but I want to go on because otherwise I don't have time. So the last point in general is related to the vegetation changes. When we wrote this paper in 2007, Cannone et al. In Frontiers in Ecology and Environment, the first reaction was, why the vegetation has to suffer of the active layer changes in the Alps, where the active layer is generally more than 1 meter thick, and you have pioneer herbs or grasses and not trees, so the roots cannot arrive to and in all the active layer. But after that, I think that the question that the disturbance that the active layer thickness increase can induce on the roots and in general on the vegetation change the winners. So there are some pioneers that can adapt very well to the disturbance and can increase. And in another case, there are some plants that are not able to suffer this increase of the movements and of the soil erosion, and this cannot escape to the higher peak of the mountains. And you can see here that in the higher part, this is the ridge and is approximately 3,000 meters high. The red colors are the areas in which the vegetation decrease in terms of coverage more in the time. But these areas here, the limit of the permafrost is already approximately at this elevation. So exactly where there is permafrost, the vegetation decrease in coverage much more than below. And if the vegetation changes, in some cases, at least this is an example from the Alps, we have also some consequence, some feedbacks on the CO2 fluxes, because the barren ground increase, and the barren ground in this area is a source of CO2, and the grasses that are the more sink plants or association of plants are decreased much more than the shrubs. And so the net balance of this is that the CO2 flux is increased. So if you look now what we know about the Alps and about the Andes, you can see and you can find a lot of modeling, a lot of maps like this one for the Alps. So we have quite a good information in terms of modeling. But if we go to downscale the modeling in a small area like in this square, the distribution change a lot because the spatial variability of permafrost is very strong. So we have big problems in the downscaling the modeling results at the real scale of the spatial variability of the permafrost in the mountain. And we have not a lot, but quite a lot of information of like this one on extracted by geophysics methods. And this is an example, but is true for the major part of what we can find, at least in the rock glacier, in the main widespread landform in the Alps, that the main part of the ice that there is where there is permafrost is in reality buried glacier ice and massive ice. And when we go there to take course, we can find this kind of ice. But this, in terms of climatic meanings, is completely different than if I can find water that freezes. This is an extinct glacier that during the Middle Age was at that position and now is covered and then is scraping down and is begin a rock glacier. So, okay, sorry, I go to just, so how many minutes I have? None, okay. So just to say that the same thing we found also in the Andes, where there are big relict bodies of ice, in this case are blue, and these bodies of buried ice are less continuous and less thick going downwards on this rock glacier. So I wanted to go just to the conclusion. So mountain permafrost distribution is still not well known, but the main important is that we have to keep in mind that we need to go much further on the ice content knowledge. Permafrost could be a strategic resource for the water sustainability, especially in the Andes, and permafrost degradation can trigger quite a lot of geological risk that can produce quite a lot of economic cost for the community. And another point that is always neglected is that permafrost degradation can improve and increase the soil erosion and the soil, the sediments load in the rivers, and this can have a cost for the hydropower plants and the dams, and also the importance, much less than in the Arctic, respect to the CO2 fluxes. Final sentence, obvious, probably, for everybody else. We need much more money to have more data to say something of serious about this problem. Thank you very much.
Okay. Thank you, and we need to close, actually. As a matter of fact, I would actually thank the streaming people for staying much longer than we had originally agreed for them to stay. If there are some questions afterwards, feel free to stay here. We will be kicked out of the room at 6, however. But I'll leave you, I think, with one thought, which is at this point in the day, the room is pretty much filled with the scientific community. And the important part of this, I think, is policy and science dialogue. And so if there's one thought in terms of the future is thinking, how do we get goodbye. The people were ready to miss their plane. We're trying to get more ideas as to how we can engage the policy community more specifically in some of the examples, some of the developments, some of the latest research, some of the latest indications of climate change in these regions, so that it is indeed well understood. I go back to the comment of Dave Carlson from IPY. Oh my goodness, they know almost nothing about what is going on, and how can we communicate that better in the future? So that is the thought and the question that I'll leave you with. Thank you very much for a wonderful day of presentations and dialogue, and we will be in touch. So thank you very much.